Okay, so in this video, we're going to talk about partition communications in MPI. But before jumping into that, I'm going to add some complementary stuff about persistent communication. In the previous video, the one that I made about point-to-point communications, in the end, I talked about persistent communication, and I shown you this MPI persistent.c, which was simply a single buffer, a single integer having the value of 42 from rank 0 being sent to rank number 1. First thing to add, I think I haven't mentioned this. MPI, communication-related operations, they have 4 stages generally. The stage number 1 is initialization, stage number 2 is starting, and stage number 3 is completion. Stage number 4 is freeing. You can hear with the syntax of persistent communications, you can see everything beautifully here. So here's the step of initialization, here's the starting step, and here the wait basically makes sure that the completion happens. So this is sort of showing the completion step. And MPI request free is when you are freeing the resources that you allocated. So why don't we see these separate steps in MPI, for example, send, which is sort of a blocking MPI communication operation, and it's in standard mode. The reason for that is because all these steps are basically merged into one call, which is MPI send. So that is some complementary note that I wanted to make. And we also mentioned that the idea behind persistent communications, as the name also suggests, persistent. It's coming from persistence in doing something. So it would appear that it should be suitable for cases that you are basically doing communications over and over, and your arguments are not actually that much changing. It might change, the buffer, for example, might change or might not change, but we haven't basically shown you this thing in a loop, a communication happening over and over. This is simply once we are initializing, starting, waiting, and then we are freeing stuff. A better example maybe is this MPI persistent that I added these two variations. This is single request version. What I mean by that, I only make one request handle. And what I do here is that in rank number 0, I initialize it with the same request. So I use one request and I initialize once, but I do communicate multiple times. Here is the beauty of that persistent communication. So you have a loop here. You're going to do some communications 5 times. Here I have it sort of stored in persistent count. And our buffer is not simply a single number 42 in the previous example, but this time it's sort of an array of 10 sort of integers. And you can see, for example, in each sort of persistent count, what we do with that, we are uniquely sort of updating our buffer. So here we use a combination of our persistent count and also the basically buffer position, whether it's going to be number 0 up all the way up to number 9 because we have 10 elements. And then we are starting, and then we can also do some computations. These examples are super simple, and the reason for that is because we want to basically show you the syntax and the general idea. And that is the most important thing that you need to take away from these sort of lessons. The rest you need to figure it out yourself based on the context, based on what you've learned from the syntax and the semantics. Then you need to basically figure out how to beautifully use these communication patterns. And after some computations, for example, you can also wait for the send to happen. And on the receiving side, more or less the same thing happens. You have the initialization, you have starting here, you can do some computations, and then this thing, MPI wait, you make sure that every message is delivered, and then you're safe to read the buffer. So let's also compile this and show it quickly. MPI run. You can see simply we are sending stuff. So this is partition count 0, and the buffer, all of them are the first 10 buffers are going to be 0 because if you remember, we had I times j. So the first one, the sort of the persistent count is basically 0. So 0 multiplied by anything is going to be 0. So that's for the first 10 elements. The next 10 elements are going to be multiplied by 1. So that's why you get from 0 to 9. The next 10 elements from persistent count number 2, starting from here, it starts from 0 for the first element, because 0 multiplied by 2 is going to be 0. 1 multiplied by 2 is going to be 2. 2 multiplied by 2 is going to be 4. And all the way down to here. And then in the last sort of persistent communication or persistent count, we have 2 multiplied by 4 is going to be 8. 4 multiplied by 3 is going to be 12, and all the way to 9 times 4, which is going to be 36. So this is beautifully basically showing persistent communications while you have them in a loop. And the next version that I have for you, if you remember, we only used one sort of request handle for all those communications, but you can also have multiple requests. So this is another version which basically uses multiple requests. So instead of having only one request, now I have an array of requests. And instead of having only one buffer, which has 10 elements, now I have 5 buffers. So I'm using sort of a two-dimensional array here. So we are having 5 buffers, which they have the same length of 10 elements. When I want to initialize my persistent sort of communications, then I pass in the buffer number I. That changes in every persistent count. And I also pass in the request sub I, or the request with these brackets I. So this is using multiple requests and also multiple sort of buffers. So the buffers which are sent here are different. In the previous case, the buffers were exactly the same, but we were updating them separately. But here we are having separate buffers. Okay. So the initialization and every sort of pattern is more or less the same. But here you have a sort of two-dimensional array. That's the only difference. Then you can do some computations, and then you start your sort of persistent communication. You don't need to wait for it. This loop is going to basically do it over and over. And then finally, you want to make sure that every sort of send operation is done. And that is why you call this sort of function wait all, MPI wait all. You give the persistent count. You give sort of the request. Make sure that the request that you're passing here is sort of an array of requests. And then we are not interested into sort of the statuses. That's why we say MPI statuses ignore. Notice the difference. It's not MPI status ignore, it's MPI statuses. The reason is because we have multiple requests. And on the receiving side, more or less is the same. You just initialize everything, and then you start it, and then you wait for it, and then finally you process the data that you have received. Let's quickly also run this one, MPI CC, MPI persistent, multiple requests, and let's MPI run it. And here's also the same, 0 multiplied by 0. All these elements are going to be 0. Then we have 0 to 9. Then we have 2, 4, 6, 8, up all the way up to these numbers here. So that is some clarification that I wanted to make with respect to persistent communication. Now let's jump into partition communications, which is the subject of chapter 4 of MPI standard. Okay, partition communication extends persistent point-to-point communications as defined in chapter 3. Partition communications operations are matched based on the order in which the local initialization calls are performed. Partition communication is partitioned because it allows for multiple contributions of data to be made, potentially from multiple actors. Either it's going to be threads or it's going to be processes or tasks in an MPI process to a single communication operation. Advice to users: the techniques of partition communication were known as fine points. Before their adoption into the MPI standard, we referred the interested reader to the original literature describing the design goals, functioning, initial implementation, and performance improvements. So if you are interested into the actual papers, which were, previously called as fine points, you can take a look at reference number 29 and 30. Partition communication operations use a persistent communication style. So you can see it's partition communication is sort of an extension of persistent communication. We're going to see the differences between partition communication and persistent communication in a second. So partition communication operations use a persistent communication style that involves a sequence of start and test or wait operations. For this sequence, partition communications use MPI start or MPI start all. This is very similar to persistent communication. And completion mechanisms such as MPI test or MPI wait. We have also seen it in previous video. Partition communication is different in three fundamental ways from persistent point-to-point operations in MPI. So this is very, very important. First, partition communication allows additional partition test function calls that can expose partial completion of the operation. So the general and the main idea behind partition communication is that you can basically break down a long message into a sequence of shorter length messages. So that is, the name also suggests it. It says partitioned communication. So partitioning means that you are breaking down something big into smaller partitions, into smaller chunks. That is the main difference in, one of the main differences with persistent communication, which if you remember in persistent communication, we are sending the whole message, the whole block of message, but we are doing that in a predictable sort of communication pattern. So, but here we are having sort of some fine tuning. We can break that one message into finer chunks of partitions of messages, let's say. So this is the first one. Second, partition communication may perform all of the initialization required to enable data transfer as early as its initialization phase. This is sort of, I think, implementation dependent as well. That's the second difference between partition communication and persistent communication. Third, partition communication allows for MPI to be independently notified of multiple contributions from the send side to a single data buffer of a single MPI message. Okay, rationale. The rationale behind having different initialization behavior allowed for partition communication as opposed to persistent point-to-point communication is to enable flexibility and optimization possibilities in implementations. That is super important. These green things are only for me because these are the important things that we want to talk about. Now we go to semantics of partition point-to-point communication. Persistent communications are opaque, use opaque MPI request objects. You already know that what is opaque request objects. Opaque is for those data structures that we said that it's sort of hidden from the client and then you can access them through handles. As described in section 3, partition communication uses these same semantics for MPI request objects. Partition communication provides fine-grained transfer on either or both sides of send and receive operations described by requests. Persistent communication semantics are ideal for partition communication. They provide MPI p send in it and MPI p receive in it. So this is the difference syntactically from persistent communications. So here p stands for sort of partition communication. So this says that allow partition communication set up to occur prior to message transfer. Partition communication initialization functions are local. So this means that the partition communication initialization includes inputs of the number of user visible partitions on the send side and receive side, which may differ. So the number of partitions that you have on the send side can be different from the number of the partitions that you have from the receive side. And we're going to see those things in a second, and you're going to understand everything so clearly. Valid partition communication operations must have one or more partitions specified. Once an MPI psend init call has been made, the user may start the operation with a call to a starting procedure. So if you want to start the procedure and complete the operation with a number of MPI p-ready calls equal to the requested number of send partitions followed by a call to a completing procedure. So a call to MPI p-ready notifies the MPI library that a specified portion of the data buffer, a specific partition, is ready to be sent. So that is that fine-grained tuning that you can do in partition communications. So you can send data with partitions, and whenever each partition is ready, you can basically send, if it's a send operation, you can send that partition, and on the receiving side, you can only sort of receive that partition and then do some computations or do something useful with it. Notification on partial completion can be done via fine-grained MPI P arrived. So this is on the receiving side. So you can check each partition, arrival of each partition with MPI P arrived calls. And also you can use MPI test and MPI wait as well. So here's nothing important. There's an example here. I'm not going to talk about it. We're going to see our own examples. Let's go to the syntax. This is sort of the language independent version. What do we need? We only need something, two things extra, let's say. We have the buffer, we have the count, we have the data type, but we have something new here. These three elements is more or less in every sort of communication patterns we have seen so far. Partitions, it's easy to understand. It's the number of partitions you have. And then we have also an info handle. That's info argument. It's also a handle. So it means that it's an opaque object. You see everything is going to be provided by us. So these are all input arguments. And then the request is going to be out. It's going to be updated by MPI psend init. So this is the initialization phase of partition communication. That's how the C binding basically looks. Here, matching follows the same matching rules that we had for point-to-point communications. It means that we are basically matching with the communicator, the tag, and the source. If communicator, tag, and source are not sufficient to uniquely identify a message, then the order in which the partition communication initialization calls are made is basically being used to eventually match those calls. This operation can only match with partition communication initialization operations. Therefore, it is required to be matched with a corresponding MPI P receive in it. So this is super, super important. Persistent communications, if you send something persistently, you can receive it with a simple blocking or non-blocking receive. So you can say MPI receive and retrieve a message which was sent with persistent mechanisms. But if you are having partitioned communication, you can only pair up partition communications together. You cannot have partition communication paired with persistent communication or partition communication paired with non-blocking or blocking normal mode, like MPI receive or MPI receive. So this is super, super important. Another difference between partition and persistent communications. And then partition communication initialization calls are local. This is similar to persistent communication as well. It is erroneous to provide a partition which has the value of less than 0. It's dumb, actually, if you do it. Send side and receive side buffers must be identical in size. Okay. And this identical in size means that it doesn't mean that the number of partitions must be equal, but the length of the message must be equal. So multiplication of partitions times partition size is going to give you basically the size of the buffer. So if, let's say, if I have 40, a buffer of size 40, I can compose it into 4 times 10. I can also compose it into 8 times 4. So 8 times 5. So 8 times 5 is also 40. 4 times 10 is also 40. So the size must be equal, but not the number of, not necessarily the number of partitions. Unlike MPI send init, MPI psend init can be matched as early as initialization call, and also unlike MPI send init, MPI send init, MPI psend init takes an info argument, which we also mentioned that was 2 things new: partitions and info handle. The rest is the same. Okay, that's what it looks like on the receiving side. I'm sorry. So again, we have number of partitions, and then you have an info handle. There's the C binding. This operation can only match with partition communication initialization operations. Therefore, the MPI library is required to match MPI P receive init calls with the corresponding P send. We already talked about this. That's a must. Another important thing is that wildcards for source and tag are not allowed. So this time around, you cannot use MPI any source or MPI any tag. This is also a very important difference. Unlike MPI receive init, MPI P receive init may communicate. Also, unlike MPI receive init, MPI P receive init takes an info argument. More or less the same as the previous advice that we had. MPI P ready is happening on the send side always. You're not going to use it on the receive side. And what you do basically is that you mark that partition to be sent, because you say, oh, this one is ready to be sent. And you see that partition is basically, it says mark ready for transfer. Non-negative integer, that's the partition, that's an input, and then you have an in-out request, that is a partition communicated request handle. That's how the syntax looks in C. MPI P ready is a send side call that indicates that a given partition is ready to be transferred. That is super, super important to know. After a call to MPI start or MPI start all partitions associated with that operation are inactive. A call to MPI P ready, so you initialize your partition communication, you start it, but after you start it, it's going to be marked as inactive. You mark it with MPI P ready to be active, and then that is when basically the sort of communication starts to, or the transfer starts to happen. And calling MPI P ready on the receiving, on an active partition is erroneous as well. Of course, you can have different versions of it. You can have a range of sort of partitions, a low range and a higher range. You can do this. I'm not going to comment on that. It's so easy to understand. Similar way, you can also have P ready lists. I'm not going to comment on that. It's so easy to understand by yourselves. Next thing is communication completion under partitioning. Again, same way, you got to use MPI wait and MPI test and other variants used to complete a partition communication operation. The completion of partition send operation indicates that the sender is now free to call MPI start to restart the operation. This is similar to persistent sort of communication. When you say MPI start or MPI start all, then you can use a sort of that request again. Subsequently, you can do also MPI P ready and MPI P ready range or MPI P ready list. Nothing important here. Then you can partially query for each partition whether you have sort of received the information about that specific partition or not. Of course, it needs a request handle, it needs a sort of partition, and it needs a flag. So this is how it looks. Notice that the request and the partition is the actual request handle and the actual partition. But for the flag, basically you gotta send sort of the pointer to the flag, the address of the flag. And you see that the request and partition are all inputs, and the flag is sort of the output. If the partition is already arrived on the receiving side, this flag is gonna basically give you the true version, the true sort of output. If it's not there, it's gonna give you the false. A call to MPI P arrived on active partition communication request returns true if the operation identified by the request for that specified partition is complete. The request is not marked as complete or inactive by this procedure. A subsequent call to MPI completing procedure like MPI test or MPI wait is required to complete the operation as described in chapter 3. So if you use sort of partial arrival, it doesn't mean that that process is marked as inactive or complete. Then you gotta also make an MPI wait or MPI test call to make sure that that thing is marked as complete, the request. Okay, so I think the rest of the stuff, yeah, these are the examples. I'm not gonna go through these examples because we're gonna go through our own examples. Let's go back and now let's see all the examples I have made for today. So the first thing is MPI partitioned. That's the simplest sort of partition communication we're going to have. Let's break this down. So here we are using macros to define number of partitions and then the partition size. So 4 times 10 is going to be the size of buffer. That is why we have for buffer 40 elements. So 10 elements per partition. That's how it looks. This is quite similar. You already know about these stuff. I'm not going to comment on these stuff because we already have gone over them. We create a request. So our request handle is only a single request. And we create a flag and we initialize it to 0. Flag, of course, we need it for whenever we want to, for example, do some checks, right? Because flag is going to be our true or false sort of a statement to do some let's say operations depending on the message being received or not being received. So we initialize it, that is MPI P send init. That's the difference with persistence. It's not MPI send, it's MPI P send. You send in the partitions, you send in the size, you send the buffer, the type is integer. You're gonna send this partition to process number 1. The tag is going to be 42. This is the communicator. And then this is the info handle. Again, similar to when we say, for example, MPI status ignore, and we are ignoring basically, we are saying MPI info null. And then we are passing in the request. And then you have to do the starting phase. So this is the second phase of the communication operations. So you initialize and then you start. So now you start to fill your buffer. And we are filling our buffer sort of, again, uniquely by combination of I and j, which is the partition and also partition size. So this is going to be different for different partitions. And then after this buffer is getting updated, you can mark them as ready with this p ready. You pass in the number of partition, the partition that is ready to be sent, and then you pass in the request handle as well. And once this thing is done, you can say MPI wait, and then you pass in the request and the status ignore if you're not interested into the status. Or there's an or here. I can uncomment this, but I need to comment this portion. I have commented this and I have uncommented this portion. This means that you can also do some computations or you can do something useful while you're testing with MPI test. And this is exactly where that flag was being used. So flag is 0, negating 0 is going to be 1. So while true, and then this thing is going to be run over and over until that partition is basically being sent over to the other side. So meanwhile, you can, I used that hamburger analogy that you can, you go layer by layer, do some communication, do some computation. And then on the other hand, on process number 1, we're going to initialize for receiving, that is p receive, and then you're going to start it. And then either you're going to wait for everything, or you can have sort of a flag and do MPI test. Again, do something useful before and after MPI test. And after we have received the data, we're going to basically, for each partition and each partition size, you're going to basically print the content of that buffer. So these are just implementation details. And one thing which is super, super important is that always notice in persistent and partition communications, you are responsible to free the resources. Here we have done MPI request free. On the sending side, that's process number 0, and on the receiving side, we are also freeing those resources, and then we have MPI finalized. So let's just compile this thing: MPI cc MPI partitioned.c and MPI run. This is done beautifully. Partition number 0. It has sort of our buffer was basically with 10 elements inside, so it shows all these zeros here. One thing which probably we have made a mistake somewhere, because these buffer sort of indices are 0, 2, 4, 6, 8. So there's something wrong here. MPI partition.c. So what is wrong here? I, j plus I times, oh, we have added j twice. You see, I made a mistake before. I thought that this thing is fine. So now I think it should be okay. MPI cc, MPI run. Okay, now it makes sense. I was wondering why is it like 2, 4, 6, 8. Now it looks beautiful. So the first sort of 10 elements, indices from 0 to 9, all initialized with 0 because we have the combination of I multiplied by j. So partition 0, 0 multiplied by everything is going to be 0. And then all the way, the next one is going to be multiplied by 1. That's why we have 0 through 9. And then all the way up until here, which is the last sort of partition being sent. So the main difference, as I said, here you might think that this is very similar to persistent communication, but the difference is that partition is one single message, but being divided into smaller chunks. So these partitions are basically all of them are making one message. So partition number 0 to partition number 3, these 4 partitions are constituting only a single message. That is very important to understand. Let's just clear the space and let's go to the one level more complicated. We're going to go to partial MPI partitioned partial.c. The idea of partial is that in the previous sort of partition communication, so everything more or less here is the same as the previous one, but in the previous one we didn't do partition checking, let's say. So you can check each partition separately whether it is being arrived or not. In the previous version, we have waited for all the partitions to be received. So in this one, we are using our flag to basically, in conjunction with MPI P arrived, we pass in our request, we pass in the partition that we are interested in. You see that I is basically representing the partitions. Then you're passing also your flag. Once you make sure this thing is going to jump out only and only if that partition number 0 in this case, let's say in the first iteration, if partition number 0 is received on the receiving side, then this flag is going to be false. It's going to jump out. Now we can process our received partition. So only and only the data inside that particular partition. That is why we go up to partition size. We cannot go through other partitions because the data is not available. So only and only that buffer, which is corresponding to that section or to that partition, that is safe to be read. And that is why we are doing here. And then once this thing is out, then we're going to set the flag to 0 again, because the next time this loop is going to basically go to the next iteration, I is going to be 1, then the flag is going to be false. Negation of that false is going to be true. It's going to wait for sort of the next partition to be arriving. So that is basically one more level of complication that you can do. Here, for example, you can again use that hamburger analogy to put some useful stuff before and after the arrival of that partition. So let's compile this example as well. So again, I'm sort of insisting on principles. You got to learn the principles. These examples are super simple because they just want to show you the fundamentals and syntaxes of these different communication patterns. Again, this thing, you see, now indices are perfectly fine. I haven't made that mistake here. Usually I do copy and paste the stuff, but this thing is true. We have a buffer of size 40 and the indices are changing from 0 to 39. Okay, now the last level of complication, which is Vim MPI partitioned partial diff. And this thing is, diff means basically having different partition sizes on the send side and on the receive side. This is what I was talking about earlier. So on the send side, we're going to have 4 partitions and the size of them are going to be 10. So 4 times 10 is going to be 40. And on the receiving side, we're going to have 8 partitions with the size of 5. 8 times 5 is also 40. So the size that these multiplications represent must be the same in partition communication, but not necessarily the number of partitions. So the only difference here is that we are using send partitions and send partition size on the send, or let's say rank number 0. Again, we are having our buffer is just 40 elements. We are sending stuff, nothing is different. We are marking them as ready, and then we are using this thing. We are testing it. We can do some computations or something useful, and then we are responsible for freeing the resources. And on the receiving side, same story is happening, but this time with receive partitions, which is different in in terms of the size that it has. Receive partitions was 8, if I remember correctly, and then the partition size was 5. So 8 times 5 is 40 again. And here again, we are checking with P arrived, the partial sort of partitions, partial arrival of partitions. And then we are processing only the partition which is arrived. And finally, we set the flag to be 0 for the next sort of iteration, so that so this while loop is going to be true. And then we're going to wait for the next partition to be arrived. So this example is also very, very beautiful because it shows you that principle that I was talking about, that the size of partitions on the send and receive sides can be different. So MPI CC MPI partitioned partial diff. and MPI run. Again, you see that this communication is basically happening. The pattern is, you see, from 0 to 39. Same principles. But this one was with a different sort of size on the receiving and send side. So there we go. This is basically partition communications in a nutshell. And again, I stress that partition communications do not exist in OpenMPI. That is why we have compiled mpeach from source, and all these examples that you saw today was basically run by mpeach MPI library. I hope you have learned something in this video, and hope to see you in the next one.